Let's say we have a weight matrix of shape 3 by 4 for now. Just ignore the bias term. We multiply the weight matrix with an input of 4 by 1, or we can say 4 neurons. We get an output matrix with a shape of 3 by 1, or of 3 neurons. We can also represent this output with this equation. Now, here you can see that each row in the weight matrix represents weights which when multiplied with inputs return one output neuron value, represented with O1, O2, and O3. Now let's take the first output O1 and try to calculate the derivative of the output with respect to all the weights. Its gradients can be represented by one gradient matrix where each value represents the gradient of the corresponding weight in the weight matrix. Now here, the first gradient can be calculated using the equation of output O1. Second and third rows have values 0 because weights of the second and third rows are not involved in output O1. Now let's take the second output in O2 and calculate its gradient matrix with respect to the weight matrix. Now in this matrix, we can clearly see that only the second row has gradient, and other gradients are marked 0 because only the second row in the weights matrix is used to determine the output value of O2. You can see this in the equation. Now similarly, we can calculate the gradient matrix for output 3. This time, the first two rows have 0 value. Now, if we multiply the weights matrix W with input I and get output of O, the derivative of output O with respect to weight matrix W can be given by this matrix. Here, this gradient matrix is the sum of all the gradients above because gradients from different directions are added together to get actual gradient when there are gradients coming from different directions. We can also get this gradient just by multiplying the matrix with transpose of input matrix. This matrix filled with ones has a shape of 3 by 1, which is the shape of output matrix we got above. This matrix of 1 is actually gradient we got as upper derivative after applying activation. Let me explain. Let's say we apply sigmoid activation on this output we got above and get some result. Sigmoid is an activation function and it can be given by this equation. The derivative of this sigmoid function can be given by this equation. If O is output matrix, then derivative of equation can be written as sigmoid of x into 1 minus sigmoid of x. Let's represent this derivative matrix with D, so we have derivatives d1, d2, and d3 for this matrix. Remember this matrix because we are going to use this in future. Now clear the screen. Let's now rewrite the equation. After applying the activation we get some result. Now we represent weight matrix with W and input matrix with I and output matrix with O and S for result after applying sigmoid activation on output matrix. The derivative of output after activation with respect to output can be written as. Similarly, the derivative of output with respect to weight matrix can be written as. Now we can represent gradient of value after applying activation with respect to weights. Then it can be written as this final gradient we got is by using chain rule. You can see it right here. We can also represent this by multiplying derivative of activation, which is represented by d1, d2, and d3 and transpose of input matrix. Now you can see that d1 is multiplied with row 1 because output O1 is generated using first row of weight matrix, and similarly for other rows d2 is multiplied with row 2 and d3 is multiplied with row 3. I tried to make it simpler, but if you are still struggling to get some intuition you can watch the video again. Now let's calculate derivatives for inputs. We calculate derivatives with respect to inputs to feed them to the previous layer for calculating derivatives of previous layers. These are 4 inputs, and now we want to calculate derivatives of each output with these inputs. Now let's take the first output O1 and calculate its derivatives with respect to each input. Derivatives for output O1 with respect to inputs can be given by. This is because output O1 is only dependent on the first row of the weight matrix. Now the same for the second output O2, we calculate its derivative. It's now the second row of the weight matrix, and this is again because output O2 is generated only with the second row of the weight matrix. You can see this in the equation. Now the same is the case with O3. Now for O3, we get the last row of the weight matrix also. Now we can represent these gradients in a matrix. The beauty of this derivative matrix is that each row represents the derivative of each output with respect to the input matrix, and each column represents derivatives of the output matrix with each input. Now if we want to calculate the derivative of S with respect to input where S is the output after applying activation, we can simply do it by multiplying both matrices linearly. Here, D1 is multiplied with the first row because it's dependent on the first output O1, which is dependent on the first weight matrix row. Similarly, D2 multiplies with row 2, and D3 is multiplied with row 3 to get derivatives. Again, we can represent this with respect to the output matrix, but this time it's the derivative of S with respect to the input, where S is the output after activation. Now to get just 4 gradients of each input, we have to add them horizontally to get the final gradient. This is the derivative of the output after activation with respect to the input. We can take the transpose of this matrix to make it look like the input matrix. The most beautiful part of this derivation is that we can directly get this derivative just by multiplying the transpose of the weight matrix with the derivative of activation we calculated before. This gives us the required derivative, which we can then pass to previous layers for further gradient of previous layers.